But before that, I would like to announce the professors. They are here today in the afternoon, all afternoon long. So available for you to discuss, to interact. So please come to us to talk. And there are other professors coming today. Professor Miro Laves, that is going to deliver a lecture next week. He's arriving today too. Bruno, for you, is very important for you because he's going to talk about quantum communication. And there is also Professor Marcus Heinrich, one of the organizers, and Anna Pedroyevich, both are arriving today in the morning, and they will be here in the afternoon too, available for you to discuss. Okay? Please.
Can you hear me? Whoop. Yeah. Well, we have good news today. We have a Nobel Prize in Physics. How many of you have read already the announcement or watched the streaming? Not many. Well, just to briefly mention it, it has been awarded to John Hopfield and Geoffrey Hinton, which were pioneers of artificial intelligence models. Particular Hopfield models are a particular subset of statistical physics models of coupled spins, and that can learn patterns. He showed how you can embed patterns in spin models and then produce an imperfect version of the pattern, and the network can relax to the right version, so it recognizes those patterns. And in the case of Hinton, out of the two concepts that they mentioned in the official announcement, I personally prefer the Boltzmann machines, which are like a statistical version of what Hopfield was doing. It's basically partition functions where some spins convey information about different patterns, and they can generate distribution. They can approximate probability distributions and do generative modeling, which is a very hot topic nowadays. To be fair, my only complaint with this is that probably all the news are going to be about artificial intelligence and not many of them about physics. So that's the only thing that I have to argue against it. But these are very beautiful works, and they deserve this prize. Let's continue with the lectures from yesterday. And we more or less left it here. I told you that we can, given a circuit, produce a quantum version of that model. And this was a roadmap of the things we have to do. It's a very abstract roadmap. What I'm going to do is I'm going to provide you with an example that is quite easy. It's simply to quantize photons. And then we will move to more sophisticated circuits. So the model we start with is the same one I showed before, where we simply pass through. It's an LC resonator. See? It's an LC resonator where you have these two linear elements creating an oscillator with a natural frequency. And I'm going to show you how we reach this conclusion classically and how we move from the classical version of the model to the quantum version. So the first thing we have to do is to identify branch fluxes and equations that relate them. So basically, you have an electrical network. And this electrical network, they're going to have some independent degrees of freedom. As I told you yesterday, we are going to assume that all the circuit elements are point-like. So if you have a certain charge distribution in this capacitor, it's just a single number. If there is a voltage difference, it's also a single number. There are not going to be spatial dependencies. So if you look at these networks, there are only 3 independent points that are this node, and this node. And for instance, this node, it will be connected to a ground plane. So basically, it has the same electrical properties as this node. And out of them, the value of the voltage here is fixed by this battery. So it's also a boundary condition. It's not an independent degree of freedom. The one on the left is fixed by the ground state, which is by the ground plane, which is normally set to 0 voltage. So you will end up with only one independent variable, which will be the voltage on this node. Quantum mechanically, as I told you the other day, we can relate voltage to the phase of the wave function. Basically, the time derivative of the phase is motivated by the Hamiltonian, and in particular by the voltage that the charges experience. So it's more convenient, instead of working directly with V, to work with a quantity, which is the electric flux, whose derivative is V. Because this quantity can be directly related, once you dimensionalize it, to the phase of the condensate wave function. And once you have this sorted out, you only have one variable. You have to find out kind of dynamical equations. For linear circuits, there are some certain shortcuts. You can simply write down the electrical, the energy of the different components of the circuit. For instance, when there is only one inductor like here, you will have this energy associated to the inductor as magnetic energy associated to the flux at this point, and is given by the inductance of this element. And there is also a capacitive energy, which is the energy that is required to charge these and these capacitors. And you can write them explicitly in terms of the flux differences along these branches. And because there is only one flux here, you can simplify everything to just these quadratic expressions. So linear circuits are particularly easy. You have to remember your theory of electrical circuits. You can write the capacitive energies, the inductive energies. And together, they give you a classical model for the dynamics, which is basically a Lagrangian with the difference of the capacitive and inductive components. This is a classical model from where we can derive the dynamical equations of the circuit, and we will eventually derive a Hamiltonian. How is it done? So if you have a Lagrangian, and you remember your courses on classical mechanics, you have dynamical equations that can be derived from the dependence of the Lagrangian on the velocities and on the positions, basically something like that. So you have the derivative of the Lagrangian with respect to your position variables, in this case fluxes, here, basically. And then the Lagrangian also depends on the velocities, the time derivatives of those variables. And from the time derivative, from the derivatives of these quadratic components, you can get the second derivative of the position, basically accelerations. And together you get an equation like this, that despite the fact that we are using ugly letters like electrical fluxes and voltages, you can recognize that this is the equation for a harmonic oscillator. It's a force harmonic oscillator. The force or the driving comes from the electric voltage that we are applying with this battery. If you make this voltage oscillate, you will simply have a driven harmonic oscillator as we are used to in classical mechanics. So this is an oscillator. It's something that we can recognize. We can find out the frequency of the oscillator, and it's going to be determined by essentially the mass that you have here, the capacitance, and the inductance that you have here. So together, omega is defined by the electrical properties of the circuit. And at this point, we can go back in history and think about how other oscillators have found quantum applications. And the most fundamental one, the first one we find, is simply the study of blackbody radiation. So Planck was investigating the electromagnetic field of inside a blackbody and what is the type of radiation that is producing outside through a tiny black hole. And what he postulated is that the electromagnetic field inside the blackbody is a collection of oscillators with certain modes and natural frequencies. And the quantization of the field means that those modes can only exchange energy in multiples of their natural frequencies. So you could take this oscillator and say, okay, I have a frequency. I'm going to assume that this is going to behave quantum mechanically if the temperature is low enough. And I will have quantum states, a ground state with no energy, 1 photon, 2 photons, and so on. And the difference of energy between these states is going to be given by the frequency I just computed from the electrical properties of the circuit. You could do that, but it wouldn't take you very far. Because this only postulates things about the energy properties of the system. It doesn't tell you what are the right observables, what is the algebra of those observables, and how you are going to produce dynamics in the circuit. So we need something else, and there is a better way to do that. I don't know why is this copied. And this is provided what is called Dirac quantization. So in the last century, when people were trying to understand quantum mechanics, one of the most important questions at the time was how we go from quantum mechanics to classical mechanics. And also, you could have the opposite question, how we can quantize the dynamics of a particle whose classical mechanics we understand. One answer was provided by Dirac. So with the understanding that we go from the quantum world to the classical world through a cancellation of those quantum fluctuations because of thermal excitations, interaction with the environment, and many other things. He understood that there is a connection between both theories, the classical theory and the quantum theory, through the Hamiltonian mechanics. Because the Hamiltonian and the equations that it gives rise to in the classical world resemble essentially the algebra that we are going to reproduce in the quantum world. And through the discovery of the canonical variables of the system. So essentially what we have to do is that if you have a Lagrangian, like the one we have here with the electric flux, with a position, with phi, and a velocity, phi dot, and you have the dynamical equations, the first thing you do is you find the canonically conjugate variable to the position, phi, through this equation. Basically, it's the dependence of the Lagrangian on the velocity. That gives you a canonically conjugate variable that in this scenario, if you understand the units, is going to be a charge. So charge is canonically conjugate to the flux. Now you do a Legendre transform to get rid of the velocities and replace them with this other variable, q. And it's very easy. You simply multiply the momentum with the velocity and subtract the Lagrangian, replacing everywhere where you see phi dot, essentially the inversion of this equation. And what you have is a Hamiltonian. It's expressed in terms of q and phi. And we make a leap of faith and say those two variables that are canonically conjugate to each other, like position and momentum for normal particle, are going to be quantized. And they're going to satisfy this commutation relation. And at this point, you have some expression of two operators defined in a Hilbert space that accommodates this algebra, and you can think about ways of doing computation with it. In the particular case we have just discussed, this would be our situation. You have a Lagrangian, which is quadratic. When you take derivatives, your momentum is simply a linear combination of the velocity and the external drive. And when you do the Legendre transform, which we should try to do this afternoon if you have time, you end up with a model that's still quadratic, where you identify the charging energy and the inductive energy of the circuit with canonical variables q and phi. So this is your Hamiltonian. The story doesn't end up here. I mean, you can end up with a quantum Hamiltonian, but if you cannot do computations with it, it's useless. The lucky coincidence in this case is that this Hamiltonian, with this particular algebra, we know how to deal with it. So if you identify q with momentum and phi with position, this is the traditional harmonic oscillator that you have studied in your degree. So we have arrived at the notion of photons through this quantization process. As a problem, I recommend that you try to redo this calculation. I will send the slides to Humberto for dissemination, and you can try to do it yourself. And I also propose that you try to do this slightly more complicated problem, which is to couple oscillators. You don't need to take pictures. I will submit it by email, and you will get it today. So it's slightly different. You can do it with the same procedure. You have to be careful, though, on how you write down the capacitive energy of this system. It's going to be a matrix, because you have a network with two independent variables. You can follow this procedure, which is also in the slides. So just to try to convince yourself what comes out. What we are going to see later on is that this is true for two coupled cavities. It gives you one Hamiltonian. And the same procedure applies also if you put here, instead of a cavity, a qubit. And the same calculations that you are going to do, we are going to reproduce them later in a different scenario. So we have light. Basically, we have microwave photons. As I told you, this is an algebra you are familiar with. You have two variables. You can adimensionalize them with suitable units. It will be the kind of natural units for the charge distribution or the flux distribution of the wave functions, which are basically Hermite polynomials multiplying Gaussian functions, things like that. No? This would be the ground state of your harmonic oscillator with some width, basically, which is dictated by this number. The nice thing is that we know how to compute everything. Basically, you have all the operators that are relevant are Fock operators. All the states that you're interested in are different photon numbers. We know how to go from one state to another through these ladder operators, but we also know how to express observables in terms of these operators. X and P are expressed as sum and differences of A and A dagger. And by definition, that tells you what are the quantum properties that you have in your circuit. So you have a full understanding of the model. You also have the possibility of putting an external potential, V. V can be time dependent, so you also know how to drive this oscillator, and you can solve everything analytically in this scenario, which is very fortunate. We can do a lot of things with this. And the nice thing is that all the quantum properties, they are determined by magnitudes that are of electric nature. So basically, you have the impedance, the inductance, the capacitance, making different quantities that will make up for all your predictions of this circuit. So these are things that are easy to engineer in the lab, and you can basically build a quantum model out of the circuit, provided the temperature is low enough. This theory extends to more exotic scenarios, and these are the ones we are going to use for making quantum networks. The picture before it was a zero-mode resonator, so there was only one variable, charge, or voltage, or whatever you want at the node of the network. You can also use this to describe cables. And electrical engineers, microwave engineers, they have done this for a long time. Basically, you have like a conductor sandwiched between two ground planes here and there, and this confines the electromagnetic field. And there are canonical models for this in terms of in-series lines and parallel inductors, capacitors, sorry. Basically, you have a model that assimilates what is happening through the cable. These are tiny inductors that describe a small unit of length with effective inductance per unit length and capacitance per unit length. And these circuits can be analyzed through a generalized version of what I showed you before. What's the difference? That now we have many nodes, you have many degrees of freedom, and the right way to a lot of couple oscillators is to go to a normal mode picture before you quantize it. So you would do the classical model, do a change of variables, find out what are the standing or propagating waves of this cable, and you end up with a model that is identical to the previous one, but now you have a family of frequencies associated to the different quasi-momenta of the waves that propagate through the cable. And you have an infinite number of modes to talk to. Once more, this whole continuum of quantum modes is described by electrical properties. In this case, you have the speed of light through the cable. That gives you the dispersion relation, which for most of these designs is almost linear. And this is defined in terms of the inductance and the capacitance per unit length, which are things that experimentalists can engineer very accurately. So you can basically engineer an electromagnetic environment for qubits or for other operations. This is, again, is a qualitative description of a very complex system. We are not going into the microscopics. And we can stretch it even further to treat even more complicated devices, like, for instance, these tubes. This would be a three-dimensional, in this case, I think it's a copper waveguide, copper microwave waveguide, where you can have flying photons through the tube. This is pretty big. I mean, might be this size, more or less. And now the electromagnetic modes, well, you would need the finite element microwave analyzer to simulate it. But you can still do that. And you can still find the canonical modes, the dispersion relations. You can still quantize this system, and you still have photons moving through this scenario. What is very obvious here is that the photons are living inside this vacuum, so it's really the electromagnetic field that moves around with accompanying surface charges moving through the tube. This is a real device that is used, it was used in the group of Gerhard-Kickmayer, and it's very nice because these are modular things that you can plug together and you can put qubits inside. So it's a very nice way of doing experiments in a truly macroscopic way. And you're going to see even bigger devices like this. Now, the next thing we need to understand is that you can drive these circuits. I told you already that you can, this voltage I put in the equation, it doesn't need to be constant. It's a classical number, but it can be dependent. It can depend on time. And in particular, we could do a typical experiment in quantum optics which is to drive a harmonic oscillator with a monochromatic field. In this case, this monochromatic field is just a microwave generated by some arbitrary waveform generator with a very precise frequency and phase that you can control in the lab, and is the circuit equivalent of a laser. So we are treating it like a C number because it's like a coherent state. You can control everything here, and what happens with that is that you can basically, with the algebra you know, you can integrate the dynamics. And the dynamics is not too difficult to understand. What happens is that your oscillator is forced. In the Heisenberg picture, you can compute the value of the Fock operators as a function of time, analytically. And this tells you that this operator oscillates with a phase, and it's also displaced with a complex number that moves in the complex plane. From A and A dagger, you can get position and momentum. So basically, what you have is your initial vacuum state is going to be displaced, and at the same time, it's going to rotate with the natural frequency of the cavity or resonator. So you know this from your physics course, and it's an electrical realization of this paradigm. Very beautiful and available in the lab. So what does this state tell you? So what is this describing? If you have read some books on quantum optics, well, what they will tell you is that this is a probability distribution in phase space. You have some average, more or less the center of the circle, that tells you the average value of the electromagnetic field components, Q and phi, or whatever you want to tell. And if you make a little bit of a tiny connection between your cavity and the outer world, and you look at the coming electromagnetic field, what you should see is basically something like this. You have something that looks like an oscillation, whose natural frequency is the resonance frequency of the cavity, and then quantum fluctuations around it, because you are measuring something that is quantum mechanical, and it fluctuates around the average values. So basically, it's something like this. You have your average value of the trajectory of this coherent state, and then a probability distribution around it describing the statistics of those measurements. You can measure it in the lab. So you can plug an apparatus. I'm going to show you how, and you can do these measurements. You can see the quantum nature of these oscillations. Until not too long ago, we were not very convinced that you could really study these quantum properties from the electrical circuit by itself. Because in microwaves, unlike in quantum optics, we don't have photodetectors. The photodetector typically is a device, a metastable device, where a photon comes in and creates a cascaded reaction of electrons that pop out and produce a signal that is really measurable. Optical photons, from the infrared to the ultraviolet, they have a lot of energy. So you can really use that to expel electrons from a material and to create these reactions. But the energy of a 10 gigahertz photons is ridiculously small. It's 10 to the minus 23 joules. So that energy is not sufficient to create a good photodetector, because that photodetector will be all the time producing noise if you use the same technology. But what has happened in the last decade is that experimentalists have found how to measure quantum microwaves. One thing that you need to realize is that there are already very good amplifiers, classical amplifiers, that can take signals that are extremely weak and make them measurable. And that is really very weak signals. But we also have developed quantum amplifiers. The superconducting circuits where you inject a little bit of energy, and it takes the electromagnetic field and applies a linear transformation that does two things. On the one hand, it amplifies the field by a factor, G, which is called the gain. Because things have to be conserved, there is this amplification comes from the mixing of two quantities, your energy and the field. There is an added noise. Fortunately, many amplifiers nowadays can have this noise to be extremely small, maybe 1 photon, when this factor can be very large, a factor of 10. So 1 photon that comes in gets multiplied by 10, and you get 1 extra photon of noise. So those signals, when you pass them through these amplifiers, and you maybe add some classical amplifiers, they are really measurable. So the experimentalists can really see the electromagnetic field inside the cavity with a high precision. The other thing that they can do is they can really measure them in real time. They can take these signals that maybe oscillate at tens of gigahertz, pass them through an electrical circuit that is nonlinear, they mix it with another signal that is very close in frequency, not exactly the same one, and what happens is that through this nonlinear process, the mixing process subtracts this carrier frequency from your signal. So it basically slows down the signal to a point that you have something that is maybe hundreds of megahertz that can be fed directly into a computer or an FPGA or whatever you want to have. So now you can do basically a quantum measurement, and by controlling the phase of the signal you mix, you can have both measurements of positions and momentum directly in the lab. And these are some plots from experimental signals that were measured in WMI in one of these seminal experiments where they create a coherent state with a certain duration, and they pass it through one of these detection processes, and they can really do a quantum measurement of the field. It's very beautiful. You can even reconstruct arbitrary wave functions like different displaced coherent states, squeeze states, cut states, single photons, as we will see, and a lot of quantum objects. So okay, I hope I have convinced you that we have access to photons in the superconducting world. Let's now try to do the matter degrees of freedom, which are the ones that we need to do quantum computing, because in quantum computing we like to have saturable media, which are like atoms. How do we move from the photon regime to the atom regime? These devices I showed you before, they are not good for qubits. You've probably seen this argument before. If you drive this oscillator, it doesn't stop in the 0 or 1 state. It goes all the way and populates all possible photon numbers. What we need to do quantum computing with many physical systems is to have an anharmonic system. That means that you have two energy levels that have a certain separation that does not coincide with any other transition of your physical system. In this particular scenario of electrical circuits, for us, it suffices to bring these upper levels a little bit down so that the energy separation between 1 and 2 is slightly lower or different from the separation between 0 and 1. If you can do that, then instead of climbing the ladder all the way up, when you inject a microwave and you start in the ground state, you will go to state 1 and down, and up and down, up and down. You will do Rabi oscillations driven by these external potentials, but you will never escape this subspace, which is our computational subspace. So we need basically two metastable states that are eigenstates, because we are going to do measurements with them, that have low decoherence, that have a sufficiently large gap so that the thermal fluctuations will not populate them artificially, and they are addressable. That means a harmonic spectrum and a couples to the electromagnetic field. The solution is a trivial modification of the circuit I showed you before. Probably it's not very recognizable in this picture. This is called a charged qubit. It's in this particular realization from the group of Yale, it's a superconducting bar. You see there? Where we can inject charge. It's a little bit like the crosses we saw in the previous quantum computer design. You can put charge. The more charge you put, the higher the repulsive energy between those electrons, and so the energy grows up very rapidly. When you couple this bar to the ground planes via Josephson junctions, what you're effectively doing is creating a nonlinear inductor that describes the tunneling of particles from the bar to the ground plane, together with a capacitive interaction that describes both the intrinsic capacitance of the Josephson junction and maybe the capacitance to the ground plane and to the central conductor. Experimentalists realized, as I told you the other day, that it's good to put qubits inside microwave cables because they are protected, but then how do you manipulate them? Well, the solution is simply to take this cable, and at some point you connect it to a voltage or current source, and this is going to be used to manipulate the qubit here, and that's described through this other capacitance and this external voltage. And that's basically the basis of a qubit. It's a very similar design to the one we had before, but we have replaced the linear inductor with this other object that is the Josephson junction. and it has different properties. It's nonlinear. So I'm not going to get into the details. So there is a suitable basis representation for this object, but it suffices to show basically what is the conclusion. The Hamiltonian, once you derive it, is going to have one capacitive energy that grows quadratically with the number of Cooper pairs you inject or subtract from the island. Why is that? I mean, if I have a Cooper pair, it takes me some energy to put it into the bar. If I have another Cooper pair, they are repulsing each other. If I have 3 Cooper pairs, I have 3 ways in which they are repulsing each other, and the number of repulsive interactions goes quadratically with the number of particles I insert. So that's intuitively acceptable, and it's also the result we got before with the oscillator, where the energy grows like Q squared. Then the other component of the Hamiltonian is a cosine of the flux that in the charge basis, it can be transformed into a tunneling term. Basically, you have eigenstates of the number of charges in the bar, and the tunneling of the particles in and out of the bar is described by this Hamiltonian contribution that is now written in different bases. It's not the basis of photons, it's the basis of charge states in the system. This is a very nice Hamiltonian because this part we understand very easily. These are simply parabolas that are shifted by the action of an external potential. This is proportional to V. And whenever 2 parabolas cross and become degenerate, the tunneling of particles between different charge states creates a level repulsion that hybridizes those states. So basically, if you focus on these first 2 curves, this will be the energy of the 0 state as a function of the external potential. This will be the energy of the 1 extra Cooper pair state as a function of the external potential. At some point, having 1 extra Cooper pair or having no extra Cooper pairs costs the same to the system. And in that point, we activate tunneling between both possibilities through the Josephson junction. So if you see, all other levels are very far away in energy space, so it's very justified to do a 2-level approximation at this point with a Hamiltonian that looks like this. This will be the charging energy shifted by the external potential and describes the energy levels of the 0 and 1 state. And this describes the mixing of those states through the tunneling of particles in and out of the bar. It's a perfect 2-level system with extremely large anharmonicity towards the 2 or -1 states and other states that the charge that the island can support. And the derivation is essentially the same one that we had before from the oscillator, but we changed the inductive potential through a nonlinear function that can be written in a suitable basis. This qubit can be controlled. Basically, you have that far away from the degeneracy point, you have very well-defined charge states. And in the middle, the ground and the excited state are plus and minus superpositions of the 0 and 1 charge states. But it's very annoying because if you see, whenever you shift the potential away from the degeneracy, the energy of these states goes up very quickly. This is a parabola, after all, it grows quadratically. And that's not good experimentally. Experimentally, when you create one of these qubits, or any qubit, in general, the environment is going to be noisy. There may be one trapped electron here that jumps from between 2 points. You can have fluctuations of the electromagnetic field in general. And so you unavoidably have fluctuations around this point. It's never a perfect control. And so if you have a very steep slope, what you end up having is a lot of dephasing. So dephasing means that the eigenenergies of your system, they can fluctuate through the experiment. And in each realization, those fluctuations are different. Imagine that the energies don't change. They are fixed. You do one realization, and this is the gap. OK, that's your evolution happens with this frequency. Then you do, and again, the experiment, and there's an electron here. Now it has changed. And then next time, the electron is not there, and it changes again. So you end up with a statistical distribution of actual experiments where you have an uncertainty of the intrinsic frequencies of your system, and you have to describe this not with a pure state, but with a density matrix. There are many ways to do that, but essentially, if you do the calculations with the Gaussian probability distribution of these fluctuations, quasi-static fluctuations, you will see that in the end, you are killing the coherencies of your density matrix, which can also be described with an effective master equation of this sort, with some dephasing rates. So that's not a very good qubit, but that was the first qubit I told you in 2004 was used to show that you could do very nice coherent experiments with superconducting circuits. What was the solution? The solution was to change the design parameters. We want to soften this parabola, make them flatter, so that energy doesn't fluctuate a lot. And in Yale, they came up with a solution. We used to change the ratio of parameters so that the Josephson energy, the tunneling between charge states, becomes dominant in the dynamics. So this would be a charged qubit where tunneling and electrostatic repulsion of Cooper pairs are comparable. You find these parabolas, very large fluctuations. If you make the charging energy smaller by putting a big capacitor on the system, you end up with this distribution of energy levels, which are almost flat. What does this mean? It means that the eigenspace, the spacing between eigenstates is almost independent of the electric potential that you're applying, but the states are not. I mean, the states, when you analyze here, are going to be different from the states here. But that's something we can live with and we can use. Mathematically, when you do that, you change the operating regime of your system, and you move more towards something that looks like this. So you have your Josephson junction gives you an inductive potential that is a cosinus, and it's not a parabola. And the eigenstates of this system, they are no longer equispaced. They are unharmonically placed, and they don't change a lot based on the external potential. This particle has a mass that is given effectively by the capacitance of the transmon, of this new qubit design, and gives rise to this spectrum that is controllable as the one for the charged qubit, but where now we have that these two levels are relatively close to this other transition that you have here. So alpha is the unharmonicity, is the frequency difference between the 0, 1, and 1 to 2 transitions. This is no longer of the order of gigahertz, like in the charged qubit. It may be a few hundreds of megahertz. What does it mean from the point of view of the experiment? We have made a qubit more stable against dephasing, but we want to do operations in a time scale that can resolve the energy difference between this and this transition. That means 1 over alpha is going to be a guide for how fast we can operate these qubits. So we made the experiments a little bit slower. Furthermore, we also have to be careful with putting a lot of energy into these qubits, because if you do that, regardless of how fast you do the experiment, you may excite the qubit and induce a process that is known as ionization. And that is very fancy nowadays because it's a limiting factor for certain tasks like measurements. So the qubit has a Hamiltonian that is still a qubit Hamiltonian, but now you cannot no longer talk about charge states. The value of the charge is a little bit diffuse, although, yeah, ground state and excited state, they have slightly different charge distributions. But we're basically taking two eigenstates, singling out and ignoring the rest. And this would be the energy separation between them. And the coupling to the environment happens through the charge operator, which in this basis has the same representation as for the photons, but it's a sigma x operator with some dipole moment in front of that. So the same circuit produces something that is saturable. It's a two-level system with a dipole moment that can be computed from the electrical properties of these elements. This is most ubiquitous, most used qubit nowadays. If you look at this plot of qubit realizations, the quality of the qubits from the point of view of the coherence has been improving steadily with longer and longer decoherence times, starting from Nakamura's experiment with the charged qubit, which had nanoseconds lifetimes. This was a very small qubit with very big electrodes making a lot of noise to that. Going through Yaris experiment where the coherence could improve significantly. And then with the introduction of the transmon, we see that we are improving all the way towards a regime where you really can do lots of operations within the lifetime of the qubit. Nowadays, the transmon, as I said, is used in all experiments from Google, IBM, Rigetti, everywhere. It's a qubit that is very useful in the sense that the fabrication of the qubit doesn't require very strict tolerances. Fluctuations of the properties from the design can be a few %, and that makes it a very useful cut and paste qubit for the lab. So how do we control these qubits in practice? Basically, the same way I showed you before. We are going to drive them. If you want to do single qubit operations, you want to do rotations on the Bloch sphere. There are two approaches. One would be to use Euler angle and compose rotations along different directions. But what I'm going to show you is that you don't need to do that. Just with a single microwave field, you can do an election of both the direction of the rotation and the angle that you make. Basically, we are going to work with this Hamiltonian. You have a two-level system driven by an external field that oscillates in time with a certain frequency and phase. Instead of doing this approach where we can switch on and off delta and omega, that will give you access to this composition of gates. I don't know what happened here. Sometimes PowerPoint does weird things. What we can do is we can transform this Hamiltonian into a rotating frame, which is where experimentalists really are thinking all the time about what happens. So you have this model, and we are going to use a rotating frame generated by sigma set with the frequency of the lasers that we use to control the qubit. When you do this transformation, essentially you are doing a change of variables. You put here a unitary that depends on time with some frequency, and you are looking at this state, not this one. So you're going to find the dynamics for chi instead of psi. Doing this amounts to interaction picture representation. The new effective Hamiltonian can be computed from the unitary very easily. And what happens is that here we have simply the frequency difference between the qubit and the drive. And here we have an oscillation. Well, they should an oscillation that is trying to cancel this cosinus here. When you expand the cosinus into both terms, that it has two exponentials, one rotating with a positive sign, one rotating with negative signs, you will get some products like e to the I minus I omega t times e to the minus I omega t. That means it oscillates with twice this frequency that are going to be negligible in the dynamics of the qubits. This is going to be averaged out. And you end up with a Hamiltonian that is dominated by these terms, like this one that cancels with this one, gives you a fixed number with a phase that you can control from the drive. So your non-Hamiltonian has a sigma set component that depends on the detuning, has an external drive that motivates these perpendicular rotations where you have the control of the amplitude and also the phase, and gives you a full control on the Bloch sphere direction where you are going to apply the rotations. The total angle of rotation will depend on how long you apply this laser pulse. So basically, you have single qubit control perfectly from just a single microwave. No, this shouldn't be here. I don't know what happens. OK. That's single qubit rotations. This is the first ingredient that we need to build a quantum computer, apart from having a good quantum system. The next ingredient is to do 2 qubit gates. And the fact is that we already discussed this kind of, the mechanism that is going to enable this from the point of view of the fact that your transmon is coupled to an electromagnetic field. So it has an intrinsic charge operator that sees the electromagnetic field. If you put 2 transmons together, they are going to see their charge distribution in the form of 2 dipolar interactions that describe the effective charges that are on those capacitors. So having two qubits together will give you an electrical interaction that is of dipolar nature. There are other qubits, like for instance flash qubits, which are supercurrents. That would be more like magnets, and they also interact like through a dipolar interaction of magnetic nature. And this is typically the qualitative picture that we can use to derive two qubit interactions. There is a more rigorous way of doing that, which is not just taking the charge operator of this guy, multiplying it by that, which goes through the problem I suggested to you before. You basically write down the whole circuit. This would be the circuit for one qubit, a circuit for another qubit, and they are interacting through a capacitive interaction, basically the capacitance between this plane and this plane. And this circuit is essentially an electrical circuit with 2 degrees of freedom, a flux here and a flux here. We can write down the Lagrangian via the capacitance matrix that describes these interactions. And this capacitance matrix has this form. It has the intrinsic capacitances of the qubits, and it has the capacitances that couples the difference of the two fluxes, basically 1 over 2c phi 1 minus phi 2 squared. So it looks like this. You have renormalized the intrinsic capacitance of the qubits, and at the same time, you have added these off-diagonal terms that is going to give you this contribution in the Hamiltonian. And that's a rigorous derivation of this dipolar interaction, which we said before. It's just a product of two dipole moment with some effective weight that depends on the separation. And that description of the dipolar interaction is embedded in the value of this capacitance that you have here. But at the same time, you are renormalizing the qubits that talk to each other. There is also a nasty consequence of this, is that if you have many qubits, your capacitance matrix is going to be very large, and it's not going to give you just an interaction between neighboring charged objects. You can get an all-to-all interaction that can be very annoying. So that has to be controlled experimentally. So if you have this mechanism where you have a charge here and a charge here, and you look at the Hamiltonians we derived before, this charge is going to be like sigma x. This one is going to be like sigma x. The dynamics is the one we were discussing the other day. Basically, you excite one qubit, and if the frequency of this qubit is very close to the frequency of a neighboring qubit, the excitations can swap back and forth between both quantum objects. This is essentially a realization of a swap gate generated by the sigma x interaction in this particular qubit. You can basically analyze this with more detail, because I mean, I have obviated many things. For instance, the fact that for this gate to work, both qubits have to have the same frequency. They have to be tuned perfectly. So if you look at this Hamiltonian, this will be the real model, where you have this, where you can analyze the dynamics of this system exactly, because it's decomposed in two subspaces. The 0, 0, and the 1, 1 states, they couple together, and the 0, 1, and 1, 0 states, they're coupled together. And those dynamics can be analyzed both in the case in which they are degenerate and when you allow for different frequencies. And you basically can understand all the gates that you're making based on this effective interaction. That's one gate. It's a very easy gate, so to say. In the quantum information world, this is not the most used gate. We tend to write down things in terms of C-nodes or control phases, like these ones. And we have to understand that despite the fact that they are formally equivalent, they cannot always be realized in the lab with the same simplicity. The swap gate I just showed you, which can also be an incomplete swap that does some entanglement, is a gate that is passive, that doesn't require energy. Simply, you are exchanging the energy between different quantum objects. The CNOT gate that you have here, if you write it down in the qubit basis, it's going to flip the state of one qubit condition on the other. That's going to change the state, the energy of the state you have created. So the engineering of some gates is more easy than the engineering of others. So to put it more clearly, so you basically have this truth table. This will be for the CNOT. You go from the 1,0 state to the 1,1 state. Here, the energy would be omega. Here, the energy would be 2 omega. So it cannot be done simply by connecting the qubits together. We have to do some kind of external drive and control of the qubits to make these artificial dynamics. On the other hand, there are other gates that are also very popular, which like the C-set gate, that conserve the energy and only contain phases. And those phases are essentially telling you that the dynamics of the states is different. Yes? Yeah, it's a typo. Yeah. 300 slides to be a typo. But, well, regardless of that, the fact is that some states change. And the energy is going to change. It has to come from somewhere. But in these other cases, you simply have difference of phases. And if you know, the dynamics of a quantum system is described by, it's generated by the Hamiltonian. What this is telling you is that different eigenstates of your problem are going to evolve with different phases. Well, H bar and H bar. So this minus sign is just an evidence of an interaction, of the fact that the 1,1 state has a slightly different energy from the 0,1 state and the 0,0 state. There is a nice way to do that with superconducting circuits. Essentially, you need to create some kind of level of repulsion that makes this state different from the rest. And for transmons, this happens, and this is used in certain quantum computing experiments. So it's something like this. You have two transmons that interact capacitively. And now we are going to allow the frequency of one of the transmons to change. In the lab, this is done through this device that you see here. It's a loop with two Josephson junctions. When you pass a magnetic field through this loop, the inductance of that junction changes. So you're basically changing the EJ of the Hamiltonian of the transmon, or alternatively, the depth of this potential. That makes the transition of the transmons move up and down in energy space and can make the transmon to be resonant or non-resonant. And if you analyze this, you end up with something like this. When the two transmons are identical, it happens what I just told you. There is a degeneracy between the 0,1 and 1,0 states, and there is a level repulsion that describes that the eigenstates are quantum superpositions of those alternatives. If you prepare the 0,1, it will oscillate to 1,0 and back and forth. If you take one transmon and move it away, what happens is that these eigenstates, they go back to the non-interacting curves. But here up, there is a coincidence. The 1,1 state of the two transmons gets close to the state with two excitations in one of the transmons. If you look at this, basically the energy of the 1,1 state has been pushed down. That means when you do the dynamics, these three states, they will acquire the same energy as if they were not interacting, but this 1,1 state will see a slightly different phase. This is another way of making gates. This was pioneered by Yale and then used by Martinez in their transmon experiments. You basically start with two qubits that are very much detuned in frequency and go down to this point and back. What happens during this time, the 1,1 state will acquire a phase that is slightly different from the other ones, and this phase can be explained as a quantum gate happening between those two level systems. There are many more gates. The quality of the gates is also improving steadily. It's already on the thresholds of what you can require to do error correction. And I'm not going to describe many other alternatives, like IBM is using CNOT gates that happen through the interaction with a mediating cavity. Or you can also do gates by putting one transmon in between two other transmons and do perturbative couplings that can be switched on and off, as Google is doing nowadays. So that goes a little bit out of the scope of this. Any questions so far? This is a lot of information. It's difficult for you not to have any questions. By the way, some of you asked for information. I put my email address on the Blackboard in case you want to get some of the PDFs or have any other requests once I leave tomorrow, so feel free to contact me. We have single qubit gates, we have 2 qubit gates, and now we have the most interesting thing for what we're going to do with quantum networks, which is the interaction between the qubits and photons. This is going to be used in this first application for measurements, basically. But the following slides are very relevant because they describe what we are going to use to do quantum links. As I told you before, we are putting qubits inside resonators because that's one thing that allows us to control them with an isolated and very stable electromagnetic environment that increases the coherence. When you take these 2 qubits and put them together, the qubits and the cavity, the model, the effective model, is again a copy of the one we have seen twice. Now, instead of having 2 qubits or 2 resonators, we have 1 qubit and 1 resonator. And the calculation is identical. You end up with a dipole interaction between the qubit and the electromagnetic field generated by the resonator. So this is basically a calculation that is in the slides for the problem I showed you before. It includes the discussion of the capacitances and so on. But for our purposes, the outcome is what matters. You have a Hamiltonian of a qubit that is slightly renormalized, Hamiltonian of the resonator, and the product of the charge of the qubit times the voltage generated by the resonator. This dipole interaction can be expressed on the basis of the qubit and of the electromagnetic field or the photons. It's a product of a sigma x and a x operator. And out of these products, the only relevant quantities are the ones that enable the exchange of excitations between the qubit and the cavity. There are going to be other products, like, for instance, sigma plus A dagger, that describe a simultaneous excitation of both objects. That is a non-resonant process, means energy appearing out of nowhere. And if this prefactor, the interaction in front of here, is not too large, we can really neglect it. So this qubit in the cavity is a perfect realization of James Cummings' model. And this is the seminal work that bootstrapped the field I showed you the other day, is that we can see the interaction between a highly coherent object, the two-level system, whose frequency we can move up and down, and another object, which is the cavity, which has a fixed resonance at frequency omega. The James Cummings model is a very nice model because basically only pairs of levels interact with each other. For instance, the level with 1 photon in the cavity and the qubit in the ground state is mapped to an excited qubit and 0 photons in the cavity. The dynamics can be fully understood in terms of these Rabi oscillations, especially when you make the frequency of the qubit exactly resonance with the cavity. For applications, we don't care so much about this resonant interaction. In many cases, we are looking for the opposite limit. We want to have the qubit preserved as possible. That means we don't want the energy of the qubit to leak anywhere. But still, we would like to look at the qubit somehow. And the way to do that is to put the qubit at the energy gap that is large, but not sufficiently large to excite the cavity. There's going to be the tuning between them. If you have this limit, you would have the Hamiltonian of the qubit and the cavity and the interaction between both objects. And you can use Schrieffer-Boff perturbation theory to find an effective model. Essentially, this is a unitary transformation with some operator G that we're going to discover, that if you look at the literature, it has this form for any number of qubits in a cavity. And when you apply this unitary transformation of the Hamiltonian, you end up with a Hamiltonian that is almost diagonal, where the resonance frequency of the cavity is shifted by the presence of qubits. The frequency of the qubit is also slightly shifted. And if you have more than one qubit, they can exchange energy between them, but it's not going to be of use for us. So what matters is this is here. So the resonance frequency of the qubit of the cavity is shifted by the qubit in different directions, whether it is in the 0 or 1 state. Here, delta minus omega is the detuning of the qubit from the cavity. It's going to be sufficiently large, but the whole product, g squared divided by delta, is going to be small. From the point of view of energy levels, you simply have energy shifts of these states depending on the state of the qubit. And these energy shifts, they can be seen in the experiment. We discussed it the other day. When you illuminate the cavity with microwaves, the reflected field is going to carry a phase shift that has information on whether it was on the one side or the other side of the resonance. So you have a setup like this, have an arbitrary waveform generator. It's connected to a resonator. Well, it should be connected the other way. And then the radiation interacts with the qubit and is reflected. And by the reflection of the microwave, we can guess the phase shift experienced by the microwave. And we can guess whether the qubit has shifted the resonance to the left, where you would see this phase shift, or to the right, where you would see this phase shift, and identify the qubit of the state of the qubit projectively. It's a measurement. It's an imperfect process. So in practice, it looks more like this. The state of the cavity that you are driving is a coherent state that is shifted in one direction or on the other, depending on the state of the qubit. And because these are Gaussians, but there is a certain probability that you misidentify the qubit state. Right now, state-of-the-art experiments, if you look at IBM's computers, other computers, have between 1% and 3% error in the identification of the qubit. That's, right now, an unavoidable error. Whenever you do a computation, it's there. You have to learn to live with it. So we put together everything, and this is what we discussed yesterday. You have qubits. You have the possibility of making them interact, measure them, control them, do single and 2 qubit gates. And this paradigm scales very well to relatively large chips. But at some point, the size of the chip is too large, and we cannot have everything on one device. So what do we do now? Well, this is basically the third part of this lecture is, how can we now take all the physics of quantum optics I've shown you here and use it to connect different devices with each other? The solution, as I anticipated the other day, is basically to transform the information from stationary qubits, like the one you have here, to qubits that you can take away in cables and propagate to different devices. So we need to understand the physics of this transaction and how it works in the lab. This is a nice point to make a break and tell me if you have any questions of things we have seen so far, or curiosities, or whatever. Everything's clear? Yep. Of what? Amplifiers, yes. Yeah, it's in the measurement part. Yep. Well, microwave quantum amplifiers are the best amplifiers right now in the whole world of quantum optics. 20 dBs is a very standard measure that you can find in the lab. Yes. One photon, yes. You may transform that photon into 10 photons. Yeah, so the noise, these are quantum limited. So they're going to be very close to 1 photon, which is the quantum limit of what you can do in these devices. So you are not free of noise, but the difference between 10 and 1 is sufficiently large that now you can take this signal and pass it through a classical amplifier. And the noise will still be there, but the difference is still large that you have a good signal-to-noise ratio. Like, you can do this identification of coherent states. You can measure a photon. I'm going to show you now a picture that was done in the lab with these amplifiers, where we can really see photons. So these are very weak signals, but once you do this first quantum amplification, then the classical amplification can really make it real-time measurements. If you don't have a quantum amplifier, you can still work with classical amplifiers, and the first experiments, they were done with classical amplifiers with a lot of noise. What happens is that then experimentalists need weeks to make averages and to get a clean representation of the things you are measuring. It's a very annoying circumstance. But let's see what is enabled by what we have seen so far. So it's until 10:30, no? That's good because it's basically an introduction to the core idea. Okay, and well, we have seen there it is. We have seen motivation to work with superconducting quantum devices and to connect them. And we have seen a little bit of quantum optics to understand how the quantum computer for this particular solid-state platform works. And now we are going to benefit from this description to introduce a quantum link between quantum processors. We have to deepen a little bit into the study of light-matter interaction, and for that I'm going to go back a step and think about how light is produced from a quantum object. So normally, if you have a spectrum like this comes from the fact that you have excited an atom by some way, probably incoherent, and when the atom releases the energy, it does it in the form of light through the different transitions it has experienced. In the superconducting world, you can do, or you can plan a similar experiment where you have a qubit embedded in a cable. By some of the means I've told you, you manage to excite the qubit, you stop exciting it, and what it's going to do is to create a photon. So basically, create something that comes out, and you can hopefully measure it. This is no different from the way you can make LEDs or other kinds of light-emitting devices. But we are going to first see an experiment where this is done. It's funny, many people have never seen an atom. So when you see these videos like the ones I showed you before, it's quite illuminating. But for sure, many of you haven't seen how a photon is produced. And these experiments with superconducting circuits, they are slow enough that we can get access to the real-time creation of a photon and the mapping of the excitation of the qubit to something that moves away. This is a picture of the experiment that I'm going to describe in a few minutes. It's a setup by the group of Gerhard Kirchmeier, where you have one of these, I think, copper waveguides, three-dimensional waveguide, where they put in the middle of the waveguide, I don't know if you can see this blob here, this is a transmon. It's a big transmon. It's something that you can really see with your own eye. And it's going to be a qubit, okay? So it's going to behave like a qubit, but it's in the middle of the way of the electromagnetic field. We are going to work on a low energy regime with not very high energy photons, where the wave function really fills the transverse degrees of freedom of the cavity. No? So the transverse profile maybe is like a Gaussian filling the square that you have here, and it advances through the tube. When this wave finds the qubit, it's going to interact very efficiently with it. What do you think will happen? If I send just one photon, what will happen? Excites the qubit. And then? Decays. And what happens to the photon? Passes through. Okay. No. It's reflected. There is a coherent process by which the photon that is absorbed by the qubit interacts with the opposite sign with a photon that would pass without seeing the qubit. And so a single qubit is a perfect mirror for a single photon because of this coherent interaction. And that's a trick we can play. So they did the following experiment. They used the technology I showed you before, where we can take the signal out of the waveguide and measure it in a glorified oscilloscope and get the electromagnetic field in time and reconstruct many properties of the output field. But in particular, they did the following experiment. So they injected an electromagnetic field, laser, coherent waveform, which is resonant with the qubit. They cannot really control the energy of this sign, but so it's going to be more than one photon. So at the other side of the qubit, we see some signal passing through. There's more than one photon, so there is signal passing through, but at the same time happens what you said. Those photons there, they can excite the qubit. So if you analyze mathematically the master equation that describes the system, your qubit ends up in an incoherent superposition of being in the ground state and the excited state. So with 50% probability, it's going to be excited. If you now stop the drive, what happens? What you just said. It relaxes, produces a photon. Because there is no drive, there is no reflection. The photon goes in both directions. And we can see it, basically. This is what we see. So at this point, we stop giving energy to the qubit, and we see a photon. There is something weird here, and it comes from this device that we have here, which is an amplifier. An amplifier works basically by collecting energy. So when you inject a signal, it takes some time to get it out. So what you see here is basically an interference between the waveform of the photon and the decay of the amplifier, and we can mathematically explain it with a simple formula. But this experiment is very similar to the atom physics experiments people have been doing, where they really send light to an electron and they see the wave packets of the outgoing photon with very accurate measurements. The difference is that we are doing this much more slowly. Okay? So if you do that, and now you change the frequency of the measurement device, and you look at different times, what you see is something like this. This would be the theoretical model. So initially, we are driving the qubit up to this frontier. This is simply the microwave signal. We stop the signal, and you see the electromagnetic field is initially delocalized in frequency space. And as the time progresses, it focuses onto a resonance frequency of the qubit, created a photon with a perfectly defined bandwidth. So this is an experiment where we convinced an atom to produce a single photon, and we can take a real-time image of as close to real-time as possible to this process. It's an amazing experiment because it shows you a coherent control of light-matter interactions with the aim of creating a mapping from an excited state to a flying photon. This experiment is very nice from the point of view of physics. From the point of view of technologies, there are better ways to do that, which require a little bit of explanation. These were pioneered by the group of Andreas Wallraff, and the goal was to create a single photon in a controlled way from a qubit. They simply put the qubit in a cavity to have a slower dynamics, and you do not need to have a strong microwave. The qubit has been excited in an excited state, and we are going to collect the photon from the qubit and let it decay to the outer world. There is a nice way to do that, which is via the adiabatic theorem. Essentially, you have either the qubit in an excited or the ground state, and you change the gap of the qubit. Before I told you we want to have the qubit far away from the resonance to protect the information, but now we want to extract this information. So we increase the gap of the qubit to a point where it crosses the resonance of the cavity. If you do this change adiabatic enough, the eigenstate at this point, which is excited qubit empty cavity, is continuously mapped into another eigenstate of the new problem, which is ground state qubit excited cavity. This new excited state has a photon that can leak out of the cavity. So if we wait, the only energy that we can get out is simply the one coming from this state. What happens if I have a superposition between the ground and the excited state of the qubit? Could any of you answer this question? What means cross? No. The eigenspace don't change. If you have a superposition, it means you have a different weight of the wave function here and here. But what is the outcome here? Who was speaking? More louder. You mean you get a superposition? What type of superposition? Exactly. So you transform the quantum superposition of excited and ground state qubit to a quantum superposition of a flying photon or no photon. This is a linear process. If you have certain amplitudes in the qubit state, they're going to be mapped into the corresponding amplitude of the photon space. Well, this is all we need to do a quantum link, so to say. It's going to be a lot of technicalities to make this into a real design, but from the philosophical point of view, this is not very different to what I was discussing the other day. Not here. Which was these people's idea of transporting information from one quantum node to another quantum node. What we have just discussed is a transduction of a stationary qubit into a flying qubit. We somehow need to do the reverse process on the other side, but if we manage to do that, we will have a perfect transport of quantum information between two quantum nodes. This requires a little bit of work. I think we are going to do that tomorrow. I just want to close with the fact that, well, this has been demonstrated experimentally. It's not just a theoretical proposal. This is an experiment that was done in Zurich in the group of Andreas Wallraff. And what you see here are different states created by different superposition states of the qubit. For instance, if the qubit is excited, it's in the one state, it produces one photon. By doing this sophisticated reconstruction of the electromagnetic field at the measurement point, they can get the Wigner function as well. And you see here the Wigner function of a single photon. If you now do a superposition with a given sign and weight of the 0 and 1 state of the qubit, where you get the appropriate superposition between the one photon and the vacuum state of the electromagnetic field with the right phases, and that will be the corresponding Wigner function for this non-classical state. So we can do that, we can reconstruct it, and it works. Any questions? Yes. This one, no? We go from there to there, okay? So this requires you to remember something I said very quickly in the other slides. So it would be this picture here. How can I? So, wow, no. This. So if you have a transmon, this is basically a capacitor connected or shunted by a pair of Jefferson junctions. You could have only one, and then the frequency would be fixed. But if you have two Jefferson junctions in parallel, you are creating here something that is called a mini squid. This squid, when you pass magnetic field through it, the inductance changes. So you are changing the depth of this potential, and you are changing the energy of the different excitations of the qubit. So you change the frequency and bring the qubit in and out of resonance with the cavity. That's a basic tool that is used in the lab. It's sometimes used to compensate the fact that you don't have a perfect design of the transmon frequency, but in this case, it's used for a quantum application. More questions, or do we need a coffee right now? I think we can stop here. Right, Elsa?